Hello everyone, I am Aditi Nigam and today I will be presenting on GaN HEMT, Gallium Nitride High Electron Mobility Transistor, commonly known as GaN HEMT. GaN HEMTs are among the most important devices in modern electronics, especially in areas like 5G communication, satellite systems, radar, and power electronics. With the increasing demand for high efficiency, high speed, and compact systems, traditional silicon devices are reaching their limits, and that is where GaN technology comes into the picture. In this, let's begin with the concept. What is HEMT? A high electron mobility transistor, a field effect transistor designed for high speed and high frequency operation. Unlike conventional FETs, we use a single material. HEMT uses a heterojunction, meaning two different semiconductor materials are combined. In GaN HEMT, the commonly used materials are gallium nitride GaN, aluminium gallium nitride AlGaN. Now, the key idea here is that this heterojunction creates a very high mobility electron channel which significantly improves performance. Coming to GaN, it is a wide bandgap semiconductor which gives it several advantages. It can handle higher voltages, it operates efficiently at higher temperatures, it supports high frequency signals. Because of these properties, GaN HEMTs are widely used in modern RF and power systems, where silicon devices struggle to perform efficiently. Now, let's compare GaN with other semiconductor materials. GaN versus silicon. The first difference is the band gap. Silicon has about 1.1 electron volt, where GaN has about 3.4 electron volts. A higher band gap means the device can operate at higher temperatures and voltages without failure. Second, the breakdown electric field. GaN can withstand much higher electric fields, making it ideal for high power applications. Next, electron and velocity and mobility. GaN allows faster electron movement, enabling high frequency operation. Another important point is thermal performance. GaN devices can handle more heat and still function efficiently. Overall, GaN provides a combination of high power capability, high speed, and reliability, which is not easily achievable with silicon. Now let's see the structure of GaN HEMT. Starting from the bottom, a substrate is used which can be silicon or silicon carbide or sapphire. Then a buffer layer is added to reduce the lattice mismatches and defects. It can be an aluminium nitride layer. Above that, we have intrinsic GaN layer. On top of it, an AlGaN layer is deposited. This creates a heterojunction interface, which is the most critical part of the device. We also have three terminals: source that injects the electrons, drain collects electrons, and gate controls the flow. The gate is placed on the AlGaN layer and controls the electron density at the interface. The actual conduction happens at the interface of AlGaN and GaN, not in the bulk material. Here comes the heterojunction, the working principle, the 2D EG channel. The operation is based on the formation of a two-dimensional electron gas. At the interface of AlGaN and GaN, due to polarization effects, a large number of electrons accumulate automatically. These polarization effects are spontaneous polarization, piezoelectric polarization. Together, they create a potential well, which traps electrons in a very thin region. This forms the 2D EG channel. Now, why is it important? Because electrons are confined in one dimension. They move freely in two dimensions. This reduces scattering. As a result, we get very high electron mobility, high current capability, fast switching. Also, this channel is formed without any doping, which reduces impurity scattering. This is one of the biggest advantages over conventional MOSFETs. So, the combination of high mobility plus natural channel formation makes GaN HEMT extremely powerful. Enhancement mode versus depletion mode. By default, GaN HEMTs are depletion mode devices, meaning they are normally on devices. This is because the 2DEG channel already exists even when the gate voltage is 0. To turn the device off, we apply a negative gate voltage which depletes the channel. However, in real-world applications, especially in power electronics, we prefer enhancement mode devices which are normally off. This ensures safety and prevents accidental current flow. Enhancement mode can be achieved using techniques like P-GaN gate recess. Referring to the graph, we see that here this is the depletion mode ID versus VGF curve, and this is enhancement mode ID versus VGS curve. Depletion mode conducts at 0 voltage. Enhancement mode starts conducting after the threshold voltage. This distinction is very important in designing circuits like switching, converters and inverters, which are important in EV applications. The advantages of GaN HEMTs are high efficiency, meaning less power loss and better energy utilization. High switching speed, which allows faster operation and reduced switching losses. High power density, meaning more power can be handled in smaller size. Low on resistance, which reduces conduction losses and heat generation. Additionally, GaN devices have better thermal stability, which increases reliability. Because of all these advantages, GaN is rapidly replacing silicon in many high-performance applications. Real-world applications of GaN HEMT. In communication systems, 5G base stations, RF power amplifiers. In defense, we have radar systems, electronic warfare. In power electronics, there are electric vehicles, EVs, fast chargers, DC-DC converters. They are also used in satellite and aerospace systems, where high efficiency and reliability are critical. So, GaN technology is playing a key role in enabling next-generation electronic systems. Baliga figure of merit, BFOM. So what is this? It is a measure of how efficiently a material can handle power. It depends on breakdown voltage, electron mobility, dielectric constant. A higher value indicates better performance. GaN has a much higher Baliga FOM compared to silicon. This means lower conduction losses, higher efficiency, better performance in power devices. This clearly shows the limitation of silicon and the superiority of wide bandgap materials like gallium nitride and silicon. This is why GaN is considered the future of power electronics. GaN's BFOM is approximately 900 times higher than silicon, meaning a GaN device can achieve the same blocking voltage with dramatically lower on resistance and switching loss. In conclusion, GaN HEMTs are an advanced semiconductor technology that offers high speed, high efficiency, high power capability. They are widely used in modern systems like 5G, electric vehicles, and advanced communication technologies. Their ability to operate under extreme conditions make them superior to traditional silicon devices. In this, we have covered about the higher band gap advantage that GaN has over silicon, the unique channel effect, the 2DEG that is happening with the GaN HEMT device, and also the system level impact that it has on the device, that is electron transistor. As future engineers, understanding GaN technology is essential for working in fields like VLSI design, RF systems, power electronics. So, in conclusion, I'd like to say GaN HEMTs are not just an incremental improvement, they represent a paradigm shift in power and RF electronics. Thank you and have a nice day.